In this video, we're going to take an in-depth look at potential energy diagrams, an important topic in our unit on chemical kinetics. We know from collision theory that in order to form products, reactant particles must collide. They have to collide with enough energy, and they have to collide at the right geometries. We also know that there's energy stored within the chemical bonds of the reactants and product particles. A potential energy diagram is going to show us the changes in potential energy during the collision process. We know that a collision doesn't instantaneously produce products. There is a process involved, and that during that process, as reactant particles collide, their potential energy increases. As their bonds stretch and as new bonds start to form, potential energy goes up. At the point during the collision when the energy is at its highest level, you have what's called the activated complex. In chemistry, a complex is where a group of atoms or particles are stuck together. So the reactant particles have collided, they've stuck together, they've formed a complex. This complex is no longer reactant particles, but it's not yet the final products. So it's in a transition. We also call it a transition state. It's going to break down and form the products in just a moment. It's usually very short-lived and very hard to study as a result. The activation energy is the energy that's required to form that transition state, to form that activated complex. So it's the difference in potential energy between the activated complex and the original reactant particles. A very, very important idea is that the larger the activation energy is, the slower will be the rate of the reaction. And that's because the larger the EA, the harder it will be to form that activated complex, and therefore the harder it will be to form the products. The difference in energy between the original reactant particles and the final product particles is called the heat of reaction, symbolized by delta H. It's the heat that's absorbed if the reaction is endothermic, or the heat that's released if it's an exothermic process. If it's an endothermic process, delta H will be positive, delta H will be negative in an exothermic process. The reaction mechanism, it describes the series of collisions by which a chemical reaction occurs. Now, it is possible for many processes to happen in one step. For example, a single reactant particle may simply decompose into multiple product particles. That would happen in one step. Or perhaps two particles collide in a single collision and form products. Or perhaps three particles collide and form products. Those would be examples of single-step mechanisms. However, when four or more reactant particles are involved, it's almost impossible for that to happen by a one-step process. Now that'll have to involve a series of steps, a series of collisions. If you imagine a car accident that occurs on a highway involving many cars, if somebody were filming that, they wouldn't find that 10 cars collided at exactly the same moment. What they would find instead is that there was an initial collision which led to another collision, which led to another collision, and that the entire accident can be described by a series of steps. So that's called the reaction mechanism. In a reaction mechanism with more than one step, there will be products of an early step which later become reactants in a later step. So those products in an early step, which are then used up later, we call them intermediate products or intermediates. In a multi-step process, one of the steps is almost certainly going to be the slowest step in the process. That step will slow down the entire process. So the slowest step in a mechanism determines the rate of the overall reaction. So it's called the rate-determining step. As we saw earlier, the larger the EA, the slower the rate. So the rate-determining step is the step that has the largest activation energy. Finally, a catalyst can be added to a reaction to speed up the reaction. It does so by changing the reaction's mechanism. The catalyst provides a new series of steps, a new set of collisions, and in this new mechanism, the activation energy is lower than the original uncatalyzed reaction. Therefore, it's a faster process. Catalysts will be reactants. They'll be added to the reaction in an early step, but then they're produced again in a later step. So they're products later in the reaction. Therefore, they get produced and released and can catalyze another set of collisions. Catalysts are not used up during a reaction. Let's now take these concepts and apply them to some potential energy diagrams. All right, in this slide, we see at the top a series of pictures that represent different points during a reaction between bromomethane, BrCH3, and hydroxide ion, OH-. In the first picture on the left, we see the hydroxide ion, OH-, colliding, or coming in rather, to collide with the BrCH3 particle. Below, we see a graph, and this graph is the potential energy diagram for the reaction above. On the y-axis, it should probably have been more properly labeled potential energy, the energy stored within the chemical bonds of the particles, and the x-axis is the reaction progress, also called sometimes the reaction pathway. We start at the beginning of the reaction here with the two reactant particles. So these are the reactants in the reaction above. At the very end of the diagram, we see the final product particles, and that'll be a bromine atom, a bromide ion rather, and then CH3OH, which is called methanol. So those two particles are our final products. Now right away I can tell something important about this reaction. Since the product energy is lower than the reactant energy, then energy must have been lost during this reaction. This would be an exothermic reaction. The difference in energy between the reactants and products is called delta H, the heat of reaction, and in this particular example, we would have a negative value. If we put some numbers on here, imagine that the final products end up with 100 kilojoules of energy. Kilojoules are a unit of energy, and the reactants began, let's suppose, at 400 kilojoules of energy. Then delta H would be 100 minus 400. It would be negative 300 kilojoules. Negative because it's decreasing, and 300 the difference between the reactants and products. Now during the collision, the hydroxide ion gets closer to the BrCH3 particle. As they get closer, they begin to interact, and so the potential energy starts to go up. At the moment of collision, when the bromine bond to carbon is stretching, and about to break, and the carbon-oxygen bond is about to form, you've reached the highest point in the diagram of potential energy. At that moment, you no longer have two separate reactant particles, but you don't yet have two separate product particles. What you have now is called the transition state. So the transition state exists at this point in the diagram at the top of that energy hill. And remember, it's also called the activated complex. As the products are about to form, the bromide bond is breaking, the carbon-oxygen bond is forming, so the potential energy drops, and in the final state, final picture, you have your two separate product particles. Now the difference in energy from the original reactants to this transition state, that difference in energy is the activation energy, or energy of activation. So we give it the symbol EA. Now in this particular graph, we've been talking about the reaction going from left to right. So we were talking about bromomethane colliding with the hydroxide ion. And so this EA that I've labeled is the forward reaction EA. However, it's quite possible that the reverse reaction could happen. There's nothing to stop the bromide ion from colliding again with methanol, and the reaction might proceed in the reverse direction. In the reverse direction, what we've called products would now be reactants, and therefore the difference here from what we've called products to the top of the hill would be the activation energy, but now for the reverse reaction. If we were to put a number for the transition state, suppose it was at 1,000 kilojoules, that transition state, then the activation energy for the forward reaction would be 600 kilojoules, 1,000 minus 400. The activation energy for the reverse reaction would be 900 kilojoules, 1,000 minus 100. Since the forward activation energy here is smaller than the reverse, the forward rate is faster and the reverse rate is slower. Here are two other diagrams, potential energy diagrams. One's labeled endothermic, one's labeled exothermic. Can you explain why? The endothermic diagram is the one where the product energy is higher than the original reactant energy, therefore delta H here is a positive value. You've absorbed energy endothermic. In the exothermic process, the product energy is lower than the original reactant energy, so now energy was released, it was lost, so delta H is a negative value in this diagram. Now, unrelated to that, we can compare the two activation energies, and we notice that the one diagram's activation energy is much larger than the other diagram's activation energy, and that would tell me that the first reaction here is slower than the second reaction. However, there's no connection at all between an EA and the delta H. It's quite possible that a reaction that is endothermic is also very fast. It's possible that an endothermic reaction is very slow as well, so the EA has nothing to do with the delta H. Alright, in this diagram there's several labels, A, B, C, D, E. Can you identify what each letter represents in the potential energy diagram? Okay, so the letter A would be the potential energy of the reactant particles. The letter E at the end is the potential energy of the final products. The difference in energy from those reactants to the products is labeled D, and that's going to be the heat of reaction, or delta H. In this diagram, since the products have less energy than the reactants, delta H would be a negative value, which means this was another exothermic process. B is the activation energy, EA, for the forward reaction, while C is the activation energy for the reverse reaction. Not shown in the diagram would be an activated complex or transition state which occurs at the top of that hill. The reactants become products, but first they form this activated complex. Now this particular diagram has only one hill. It has one activated complex. Therefore, that represents a one-step reaction mechanism, and that's all we've seen so far. In this new diagram, we can see a multi-step reaction mechanism. In fact, it's a mechanism involving two steps. Two steps because there are two hills. There is step 1 and there is step 2. We have the original reactant particles and we have the final product particles, just like before. Now in this diagram, the difference is labeled delta E, but we've been using a different symbol, so I'll be consistent. Delta H, which is the heat of reaction. It's again an exothermic process overall because the products have less energy than the reactants. So delta H overall is a negative value. At the top of the first hill, we have the transition state number 1, the first activated complex. At the top of the second hill, we have another transition state, another activated complex. The first step's activation energy is here, And the second step's activation energy is this little arrow here, because the second step begins at this little bit in the middle and goes up to the top of that hill. So there's EA for the second step. Now, in between the reactants and the final products, we have intermediates. The intermediates are the products in the first step, but they're the reactants in the second step. So you could define here the intermediates to the top of the second hill, the intermediates to the second transition state. That'll be your EA in the second step. Now, the first step had a delta H that was here. That's the delta H for step 1, the difference between the reactants in step 1 and step 1's products. And notice that step 1 is endothermic, and rather large endothermic. Step 2, though, begins at the same intermediates and finishes at the products. So step 2 would have this delta H. That would be delta H2, and delta H2 is exothermic. If we add delta H1 to delta H2, we get this, which is the delta H overall. Okay, it's the difference between the original reactants and the final products. Now in this diagram, the first step has a much larger EA than the second step. So the first step's activation energy is much larger. That makes it by far the much slower step of this two-step process. Therefore, step 1 would be the rate-determining step, the slowest step in the reaction mechanism. All right, on this slide, we're going to take some information that's been given on the left, and we're going to try to sketch a potential energy diagram on the right. If you'd like to pause the video and try this yourself, that'd be great. So just glancing at the information, it appears that this is going to be a two-step reaction mechanism. That's because there's an EA1 and an EA2, a delta H1 and a delta H2, an activated complex 1 and an activated complex 2. So there's several clues there that it's a two-step process. So we're going to have two hills in the diagram. The original reactants had an energy of 300 kilojoules. So I'll draw a plateau here and I'll label that R. The final products have an energy of 650 kilojoules. So way over here at the end, I'll draw another plateau at 650, and there's my final products. Now right away I can tell what delta H overall is. That's letter F, and notice it's blank in the information because I can actually deduce it from what I've just drawn there. The delta H overall is the difference from the original reactants to those final products. So from 300 up to 650, delta H overall is positive, and therefore it's positive 350 kilojoules. Right? From 300 up to 650, the difference is 350. So there is delta H, and I've run out of room, but overall is what I would write beside that. Now, we don't know the potential energy of the intermediates. The intermediates are going to be a plateau somewhere in the middle of the diagram, but we don't know it, so we're going to have to figure that out. Step 1's delta H, the difference between the reactants and those intermediates, is also not told to us, but step 2's delta H is told to us. Step 2 was an endothermic process with a delta H of positive 200. Now what does that mean? Well, step 2 begins with the intermediates and finishes with these products. Since step 2's delta H was positive 200, the intermediates must have been 200 kilojoules lower than those final products. If the final products are at 650 kilojoules, then the intermediates must have been here at 450 kilojoules. Just to see why, again, the difference from those intermediates to those final products is delta H for step 2. And so since it was positive 200, we know that the intermediates had to be lower energy than the final products because there was an increase in energy between them. We can now say what delta H1 was. It's the difference from the reactants to the intermediates. delta H1 is also endothermic, and so if they began at 300 and finished at 450, delta H1 would have been positive 150 kilojoules. And notice that if we add delta H1 to delta H2, we get delta H overall, so I'm pretty confident that I've got those right. Now, part G tells us the activated complex energy for step 1 was 550 kilojoules. So the activated complex occurs at the top of the energy level for step 1. So here at 550 kilojoules is the AC number 1, and that could have been called the transition state also. So now there is the first step of the process. I could now label the difference between the reactants and the activated complex. That's my activation energy for step 1. Since they began at 300 kilojoules, the reactants, and went up to 550, EA step 1 must be 250 kilojoules. The second activated complex is not told to us, but we know the second activation energy is positive 300 kilojoules. Step 2 begins with the intermediates at 450, so if the EA was 300, they would have gone up to 750 kilojoules. So here at 750 is AC number 2. And so the second step, go from the intermediates to that activated complex, and then back down to the final products. The difference in energy between the intermediates and the second activated complex is the EA for step 2. And so now we've got pretty much everything labeled. The second activated complex was at 750 kilojoules, and our intermediates were at 450 kilojoules. Now, which of those two steps, the first or the second step, was the rate determining step? To answer that, we just look at the activation energies, EA1 and EA2. EA1 was 250 kilojoules, EA2 is 300 kilojoules, so therefore step 2, which is here, step 2, is the rate determining step, because its activation energy, 300, is larger than step 1's activation energy, 250. The overall process was endothermic, and both steps were also endothermic because the delta H's are all positive. So there's a good example of sketching a potential energy diagram. The last topic in potential energy diagrams is to look at the effect of adding a catalyst on the diagram. A catalyst, we said earlier, speeds up the reaction by changing the mechanism. Now, how it changes the mechanism will change from reaction to reaction. There's no one way that they do this. In this particular diagram, the green curve represents the original uncatalyzed reaction. So notice the reactants were originally here and the final products are here. The final products, I just wrote an R when I should have written a P. The green curve shows that the original reaction was rather slow because it had a very large activation energy without a catalyst. The transition state was way up here, a very high energy transition state. Delta H was negative. It was an exothermic process. It was a one-step process because there was one hill in between the reactants and products. Now, when we add a catalyst in this example, the red curve is produced. So the red curve shows that this catalyst changed the mechanism from a one-step process to a two-step process. Now, some catalysts may not change the number of steps. It's possible that the catalyzed graph would have also one step, or maybe the catalyzed curve has 3 steps. The point is that the catalyzed reaction has a different mechanism, and there's not going to be one way to apply that idea. It may have one step, but be a different step. It may be now 2 steps instead of 1. If the original reaction was 2 steps, perhaps the catalyzed reaction is now 1 step. It changes the mechanism. What must be true in the catalyzed process is that the overall activation energy, which would be the difference from the original reactants to the top of the highest hill in the catalyzed reaction, so here EA2 is the overall activation energy in the catalyzed process, it must be smaller than the original activation energy in the uncatalyzed reaction. Why must it be smaller? Because a catalyst, by definition, speeds up the reaction, and the smaller the EA, the faster the reaction will be. In this diagram, the EA for step 1 is here. I just realized this diagram is mislabeled. The EA for step 2 would actually be starting here and go to the top of that hill. That would be EA2. What was labeled EA2 is the overall activation energy for the catalyzed reaction. The difference from the reactants to the top of the highest hill is the overall activation energy in the multi-step process. But step 2's activation energy would have begun here at the intermediates and to the top of that hill. That's more properly called EA for step 2. So the catalyst diagram starts at the same point, finishes at the same point, so delta H is not affected by a catalyst, but the number of steps may be changed, and the EA of the overall process must be lower than the original activation energy of the reaction. So there's how a catalyst may affect a potential energy diagram. So that's an in-depth look, a rather detailed look at potential energy diagrams. This will make up about 20% or so of your unit test in chemical kinetics. So be sure that you are really strong on this topic.